I know that we've got a bunch of Postgres users, that several of you are Postgres users. Anybody here not a Postgres user? Oh, there we go. Kinda, okay. How many people here use Docker and other container tech? A couple, okay. Well, one way or the other, let me go ahead and get started. So welcome, late afternoon Sunday sessions. I was a little lightly attended, particularly when you're up against some of the people I'm up against. But I think you'll find this worth your time. I'm going to be talking about doing high availability stuff with new tools for PostgreSQL. For our one non-Postgres person, this could be adapted to other systems and probably will be. But right now it works for PostgreSQL. So rather than just starting into a long description of the architecture, I thought it would be more fun to just show it to you at work to start out with. Because there's been a lot of Postgres HA stuff in the past that has involved a lot of hand-wavy description of how things work. And instead, I think I want to show you an actual working system here. Now, mind you, it's not a real production system because I'm running all of the containers on this laptop, which is not what you would do in production. Obviously, you'd have them all running on separate machines. But it does make for a good demo. So, first thing I'm going to do here is I'm going to use Docker Compose to bring up my containers. And let's tail the Docker Compose log so you can actually see what's going on here. Ooh. There we go. Okay. We're getting a lot of stuff, and so we're getting reports from two of the nodes there, as you can see in the bottom, nodes 3 and nodes 1, that they've bootstrapped from the master. We're getting feedback that those two are secondaries. So let's see, do we have a replication cluster here? Let's see. So we've got, here are our containers running right here. We've got 3 database nodes, 1 etcd node. I'll explain what that's doing further in the presentation. Looks like node number 2 is our master, so let me find out its address. Okay. So we're going to log into that. And looks like it has 2 replicas. So we've got our cluster with 1 master, 2 replicas. Right here. And we are up and running. So, but of course, I'm here to demonstrate failover, right? And high availability. So let us kill off the master. Okay, so again, 2.1 is node 2 is our current master. So we're going to stop it, and you see a whole bunch of activity there. This is all log output from the Patroni system. Ta-da. And then we get a whole bunch of stuff here. Wait. And we can see the other 2 nodes restarting. So we try to do this again. Oh, we don't have a connection anymore. Oop. Hold on, it's got a hold of the cursor and doesn't want to let go of it. Just a moment while it TCP times out. Okay. So let us connect to, I think this is going to be number, oh, no, wrong one. Who's the master here? I'm the leader with lock 3. So there we are. And you can see that now node 1 is streaming from node 3, which is the new master. So this is the essence of our system. There's a lot of code that went into making that happen. And so now we're going to talk about that. In the meantime, we'll leave our 2-node cluster running. Since we do have a small group, feel free to interrupt with questions. Although at this point, I haven't even started to describe the architecture. So, yeah?
You did bring them back up the node that you shut down.
Oh, right, yeah. Actually, no, hold on. I meant to do that as the demo. Let's go ahead and bring that node back up, hey? It would become a slave. And let's do that. Thank you for asking.
Actually, we're in
Okay, so I just restarted DB node 2, and you see we've got a bunch of stuff going on there. It's looking for a replication slot. It can't find it, and so it creates a replication slot. Replication slots are a feature of Postgres 9.4. They're really useful, which is why we create them by default. And now, if we look over at the master, which is still DB node 3, it now has 2 replicas, because DB node 2 has restarted and rejoined the cluster as a replica. And that would work whether we were instantiating a new DB node 2. If you're restarting the old DB node 2, that would only work if there wasn't any trailing replication information, unless you're using the PG Rewind plugin, which I'm not going to cover in this particular session because it's new. So that's operation in a nutshell. So now let's actually describe how that worked and why it's needed. So I'm going to first start out. Postgres' built-in replication is really cool. I'm really happy with it. It took a number of years to hammer out, but at this point, it's easy to set up. It makes all kinds of guarantees about replicating your data. It prevents data corruption. It prevents a lot of sort of common foot guns with replication. That is, you have to really try hard to fuck up your systems. You know, the worst that'll happen is you'll break replication will stop working, right? And you can combine it with disaster recovery fairly easily. Have a replication and disaster recovery in one mechanism system. So you think, hey, all of this is great, but we're kind of missing something, which is, why is there no built-in failover? I mean, MySQL has built-in failover, right? Well, sort of. And this actually has led to a number of things, including I actually heard this at a recent conference. I forget which conference I was at in the fall. Somebody was actually talking to a Postgres person in a Postgres booth. And they literally said to them, automated failover is too complicated, you don't want it. Well, no, that's not good enough. A lot of us have SLAs to meet. We have always-on applications. And it's not impossible. Automated failover is doable, particularly if you restrict the problem. Now, part of the problem that we run into in the Postgres world is we try to solve everything for everyone. And coming up with a failover system that will work for absolutely everyone, no matter how they're using their database or what they're using it for, or what hardware or environment they're running in, is in fact pretty close to impossible. However, coming up with a failover system for how a lot of people use their Postgres databases, these days anyway, which is a bunch of OLTP or web databases running in some kind of a cloud or container environment, where we can have a pool of asynchronous replicas and automatically promote one when the master goes down. And we have the ability to have some kind of a watchdog node. These are sort of our prerequisites here, right? Is that this is going to be sort of our system. And it turns out that this particular set of requirements meets the needs of a lot of people. Not everybody. There are people who need synchronous stuff and guarantees against data loss. There are people who can't, have to run on large hardware where the point of spinning up a new node is prohibitively expensive. But an awful lot of applications here fit this spec. So now, I wrote out that sort of spec a few years ago and then worked with a team of my former coworkers at Postgres Experts to build a system called HandyRep based on this set of requirements. So HandyRep is a master controller architecture. It's built with Python Fabric and SSH. It's in production in at least one place that I know of. It's been forked a couple of times, so I don't know if it's in production elsewhere. And the idea was, because we were a consulting shop, to build something that would work with any of our clients' Postgres configurations in place as they were, which often involved dealing with a lot of really screwy stuff in terms of LDAP authentication and special subdomains and all kinds of other things. It was also designed to be pluggable in order to support all of these infrastructure changes. So we worked on that for about a year and a half, pretty much completed the initial spec for that, but there were some problems with it as a general solution. You pretty much had to have us install it for you. It was difficult to install. It was really difficult to debug in terms of when we would lose a replica out of the system. It was really hard to figure out why. In the end configuration, it had over 100 different configuration options, possibly more depending on plugins. It scaled kind of poorly. Like, it was great for like 2 to 4 node, maybe 6 node clusters, but beyond that. And the HandyRep server itself as a master controller was kind of a single point of failure. Like, we could have a secondary HandyRep server, but it was manual failover to that. And that wasn't helpful, but we couldn't have 2 because then we had potential problems. So it was like, okay, part of the problem with the HandyRep design was that we were trying to be too general. We were trying to tell our clients, you don't have to change anything about how you're doing Postgres. We'll retrofit a failover system on top of that. And that is what some people need, but it's not a general downloadable solution. I really wanted a general downloadable solution. Well, in the meantime, there's this company called Zalando. And Zalando is like the #1 European fashion portal. Hold on, I'm trying to figure out a way I can put down my coffee without it falling over. Okay. Zalando is the #1 European fashion portal. They've got about 15 million customers, ship some ridiculous amount of merchandise per week. They have 150 Postgres database nodes in their environment and have to be 24/7, 365 because they control their own shipping, not just online sales. So, allowable downtimes are tiny. And for that reason, they needed automated, decentralized, high availability. They'd look at HandyRep, but they felt it didn't fit their needs because, among things, they needed to support much larger clusters. They needed to be a lot more autonomous and not dependent on the DBAs to configure them. So while Zalando was looking at this, and while I was getting dissatisfied with not being able to make HandyRep portable enough, some stuff happened. Now, Zalando ran into a lot of the common problems that you have. They had they tried to do it on their own, and they ran into a lot of the common problems that you have with automated failover and high availability, right? False failover, where you failover when you didn't need to, which is always problematic because you have to break a bunch of application connections, have to reconnect, and if it's happening all the time, that becomes a bad experience for the user. Misfires, where you try to failover and you can't complete it. Race conditions, where you can't figure out who the new master is supposed to be, and you either end up with 2 or none. Those sorts of things. And then they ended up with, and they encountered the worst problem with automated failover. Does anybody know what the worst problem with automated failover is? Yeah, exactly. Split brain. So OpenX kindly supplied me with this little brain. So we got split brain here. Here, have half a brain. Oh. And here we go, have half a brain. Ta-da. So split brain. Yep. Split brain is our big problem with that. And that from the perspective of people who are approaching this from a transactional database where consistency is considered important, split brain is kind of the worst place you can end up, right? It's actually usually better for the system to be down than to have a substantial risk of split brain because there is no automated recovery from split brain. And under some catastrophic circumstances, no recovery at all. So, what we really needed was, we needed a service that could come in and bless all of our little cloud Postgreses. Those are little flying elephants, if you can't tell. bless all our little cloud postresses, bless one of them as the master, and if that one goes away, bless another one as the master, and be consistent and immutable and independent about it. So while we were thinking about all of this, a company called Compose.io, which was an online hosted, cloud web application as a service project, they're about to be acquired by IBM. And before the acquisition, they open sourced a bunch of their stuff, including the system that they use to provide high availability for Postgres. Not the complete system, but the initial proof of concept that they did that became a system when it got integrated with their architecture, et cetera, right? And they open sourced that, and it was called High Availability for Postgres, Batteries Not Included, was called Compose Governor. Now, this was just a proof of concept, but it was the ideas behind it were really good. And part of it was that they used a lot of, at that point relatively, this is about a year ago, they used a lot of, actually it's not even a year ago, God, 6 months, 7 months ago? Seems like a much longer time. But they used a lot of technology that was just emerging, right? So Linux containers, etcd for consensus, and a simple Postgres controller that lived on each node. And so we forked it. Zalando forked it. I started contributing to it into a new project to actually make it production worthy. So now, that's our background. Let me explain how it all goes together. So you actually understand the new system. So the first thing to actually understand about this is that there's actually 3 parts to database failover. Part number 1 is detecting when you need to fail over. Part number 2 is actually failing over the database, and the third part is failing over the application from one database node to another. Now, in the current Patroni system, part number 1, detecting failover, is handled by timestamps with an etcd. Again, I'll explain etcd in a minute. And API checks on the individual nodes. The clock switches have to be consistent on the etcd cluster. And actually, honestly, if your timestamps are wildly out of whack in your database cluster, you're going to have other problems as well. That won't go undetected for long. The second part is what's called leader election with an etcd in order to decide who to fail over to, and then, of course, Postgres replication failover. The third part, failing over the application, is not yet handled in Patroni, although I'll talk about how that's handled by external systems later on. So here's how it works. So we have our little Postgres node running in a Docker container. So here's our elephant in a Docker container, right? Now, that's not just running Postgres in the Docker container. In fact, it has this little Patroni daemon, which is a pilot. And the Patroni daemon actually controls if Postgres starts and stops and controls its configuration. The idea being that if Patroni isn't running on that node, neither is Postgres, period. This was one of the big problems I had with HandyRep, is that I ended up with all this complicated logic of, okay, how do I detect if Postgres is actually down or if it's just HandyRep that's down? Well, the answer is we set it up so that it is not possible for Postgres to be running if the Patroni node is down.
Is the container absolutely necessary for this to happen?
No, you can actually set this up on VMs, and you can even set it up on real hardware.
Yeah, no, you just had mentioned the container.
Yeah, it's a lot, containers actually encapsulate this a lot better, but no, I believe Zalando's doing this on VMs. And so then you've got one of those, and you've got a whole group of these, right? So a whole group of our little Postgres containers piloted by Patroni in each case. And so this is just a little Python file running as, in this case, in the container case, this is running as the application of the container. The nice thing about the container approach is you don't have to take extra mechanisms to make sure that if Patroni shuts down, Postgres shuts down. Because in a container setup, if my application for the container is Patroni, if that application stops, the container stops. And that's controlled by the container infrastructure. If you're running this in VMs or real machines, then you would actually need to do some extra stuff with, say, systemd to make sure that if Patroni exits, that the Postgres postmaster exits as well. And that's the advantage that running this in containers buys you, even if you're going to have one container per machine. So then what happens is we say, okay, well, we've got we've just started up 3 co-equal Postgreses, so how does this become a replication cluster? Well, so what happens is these 3 co-equal Postgreses, we need one other element here, which is an etcd cluster. etcd is a distributed, consistent key value. It's actually more of an HTTP information store. I'll talk a little bit more about it later. Let's just understand how it functions right now. So etcd, we've got an etcd cluster here, which functions as a single consistent service. And so what happens is when we start up our nodes, they all send messages to etcd requesting to be the master. And etcd holds what's called a leader election. And it decides one of those wins the master election. And it sends messages back to them and says, okay, node 2, you're the master. Nodes 1 and 3, you are replicas, and your master is node 2. And so then we do an automated base backup from node 2 in order to make node 1 and 3 replicas. Yeah?
So like if you had somebody drove a car into a power pole and got the power to the entire, does it remember which one used
Yes.
the master?
Yes, it does. etcd does, in fact, store its data, and it writes it synchronously to disk.
Otherwise they
So this does recover from being down. Although you might see a whole bunch of failovers if the system doesn't come back up all at once, which is often the case, yeah?
Just curious, I know that with etcd you don't have like an op number before. Is there a reason you do like an op number?
It could just be 2. It could just be 2, it could be 5, could be 15, whatever you want. Yes, no. There is no particular one. It's just that 3 is good for a demo because it's enough that I can actually demonstrate failing over without enough that I use up all the RAM on my system. So anyway, that's establishing the initial cluster replication for a brand new cluster. Now, if you were retrofitting this onto existing Postgres servers, you would have to actually take some extra steps. But if we're doing it as a blank canvas, I'm going to load everything via PG restore, then you just do this, right? So then the question is, what happens when we lose the master? As I just demoed, right? We lose the current master. Well, what happens is all of our nodes are sending messages to the etcd server every 10 seconds in the default configuration. You can configure that interval. They're sending every 10 seconds. Those notices have a time to live of 30 seconds. So after 30 seconds, they're going to check etcd and discover that there's no longer a master. Hey, no master exists anymore. And then what they're going to do is that one of them, whichever one happens to do it first, is going to try to grab the master key. So now, during a failover, this happens in 2 stages. In initial deployment, whoever grabs the master key first gets it. In a failover, we want to be more discriminating. So what happens is, whichever one does it first tries to grab the master key. It gets a temporary lock on the master key, and then it checks the replay point of all of the other potential failover nodes using the Patroni API. Because each one of these Patroni daemons, I forgot to mention, each one of these Patroni daemons not only controls Postgres, but it also has a RESTful API that is used for some of the operation of Patroni. And so over the RESTful API, we can query what the replay point is on each one of the different nodes. So if, for example, one tried to grab the master key, and then it checked the replay point on node number 3 and it discovered it was behind, it would give up the master key. At which point number 3 would grab it and promote itself to master. At that point, so that's the election process. It's a 2-stage election process for failover. At that point, we send back a message, etcd confirms you have the master key, you don't have the master key. And then the node that doesn't have the master key changes its primary connection info, it changes its replication source and starts replicating from the other server. And we failed over. Any questions about that so far?
What happens in like the ultimate
That's a very good point. So let me actually talk about this a little bit more when I talk about split brain, because that's exactly what this goes into. So here, wait, hold on, we've got another brain to split. Who wants half a brain? Have half a brain. Anybody else want half a brain? There we go. Oh. Yep. So, because I haven't actually talked about how do we prevent split brain. Well, in this case, we're actually relying onto a lot of groundwork done in etcd. For those of you who are not familiar, because most of you did not raise your hands earlier at being, anybody, some people work with etcd and similar services. Console, Zookeeper, yeah. So etcd is a distributed consensus HTTP data store. It stores all of its data as HTTP paths. So it's kind of a document store. It uses the Raft algorithm, which is one algorithm for what's known as distributed consensus. The Raft algorithm is designed to implement in the CAP to implement CA, right? As in, it's consistent, it's available, it is not partition tolerant. As in, and I'll show you that in a minute. etcd is great for configured information and metadata. Because when people say, hey, if etcd is able to maintain consistency across a cluster, why not just put our database data in there? Well, here's one of the problems. It's really friggin' slow compared to like a transactional database. Like, the number of writes per second you can get in etcd is measured in like the tens. Because it's doing this whole consensus thing on the back end. So you don't want to store real data in there. And as a matter of fact, we go to some trouble within Patroni to only write things to etcd that need to be there versus things that we can pull the API of the individual nodes to get. Because like initially I had this design where I was constantly updating the replay point in etcd. Turned out not such a good idea. When you're running etcd on a really lightweight container where there's a lot of other stuff, it can be a problem. So, now there's some alternatives to this. People familiar with Zookeeper, which tends to be a little bit larger scale. It's the big Java-based thing. There is support for this in Patroni. You can run Patroni using Zookeeper. Console by HashiCorp is the other one. And that actually has this nice thing of integrating discovery services as well. There is not currently support for that in Patroni. We don't have the module for that, yeah?
It's implied by all those nodes register with store, right? You don't discover that by some
No, that goes into the Patroni configuration, which I'll show you in a minute. Initially, I actually had a mission to support console. I was writing a console support module, and then that use case went away because that particular user switched to Zookeeper. So if somebody else wants if someone wants console support, they're going to have to write the module. Shouldn't be too hard. We've already got examples of how you do both Zookeeper and etcd. Anyway, so the idea of etcd with a distributed consensus thing is if we actually have a network partition, then the etcd cluster knows if it can't establish communication among a majority of the nodes that were originally in the cluster, then it responds with failure messages to information requests rather than providing the information. And that's deliberate. And that means that we prevent split brain due to a net split because any database nodes that can only connect with the stub of the etcd cluster will get back failure messages. Now what happens with Patroni when they get those failure messages is that database node will reboot in read-only mode if it was read-write. If it was already a replica, it will just keep going. Because the problem is, if that was our original master but it's now in an isolated network segment, we do not want it to be continuing to accept writes. But it's okay for it to be up to continue to accept reads. I mean, we'll get stale reads, but presumably in a net split situation, somebody is getting pager alerts. And presumably we're going to actually straighten out the application connections at some stage. And so that's basically how it sets up. For etcd, this means that your cluster is statically sized. Changing the size of the etcd cluster requires a restart of the cluster. I believe, which is a little bit annoying because obviously during the restart of the cluster, you're going to have a flip over in Postgres and a master election. So give it some thought. I mean, the thing is the useful sizes for an etcd cluster is usually about 5 nodes, if you're really trying to guarantee against, failure situations. So there's not a strong reason to make it larger than that. Zookeeper, I believe, can be actually dynamically resized. It uses a different algorithm for consensus, but it does perform a lot of the same functions. Yeah?
So if the meter fails, you said that in the election, the replica that's furthest ahead wins.
Yeah.
But what if the furthest ahead replica is itself behind the meter? You just accepted it lost some data?
Yeah, well, if we're doing asynchronous replication, yes. Under any failover circumstance with asynchronous replication, you will have lost some data. Yeah. If you can't afford any data loss, then you'd need to set up synchronous replication. We have within Patroni, we have some configuration options for synchronous replication. I'll warn you that I don't think anyone is using them. So test the hell out of that if you're going to actually go that way right now. In general, for a lot of the stuff we're talking about, webby stuff, we're willing to accept the loss of a couple of seconds of data versus being down for an hour while we wait for a human being to check it out. That is, however, another reason to not actually restart existing nodes automatically. There's several reasons. First of all, if the node failed in the first place, you don't really want to restart it automatically because you don't know why it failed in the first place until a human looks at it, right? Second thing is, if the node failed in the first place, it has untransmitted data. If you restart it and force it to rejoin the cluster, you're going to wipe out that untransmitted data. Whereas if a human being restarts it, isolates it from the cluster, they could potentially recover some lost transactions. Yeah. So let's look again at the setup in detail, now that you actually know what it's supposed to be doing. So first of all, I mentioned that each one of those nodes is running a Patroni daemon. So this is actually the configuration. So you configure Patroni on each individual node, and you pass it along configuration. This is the configuration that's getting loaded through Docker Compose into each node. The placeholders are for environment variables that are being loaded through Docker Compose. So we actually want to take a look at that. There's a few of these things. So scope is somewhat cryptically named. It's the name of the cluster that you're running it in. The idea is that you may have multiple database clusters in a single network, right, that you're running Patroni on. They may even share etcd or Zookeeper servers, in which case you actually need to have namespaces for each of them, and that's supported. Default time to live, default polling interval right here. And then we've got some other configurations. Like I said, there's a REST API running in each node, and so this is where you tell it what IP and port it's going to be listening on. Within that, what the advertised connection address is going to be. The reason why these are two different lines is because if you're doing some sort of network redirection or network masking, particularly for, say, service discovery, your advertised address from outside the container or the VM might actually be different than how that address is seen internally. And we need to support that. Most of the time, these are going to be the same. So currently, the API supports SSL and simple statically set user password authentication. We haven't had a strong push for supporting something like LDAP or whatever for the API. So again, if that's something that you need, fork the project. That's what it's there for. And then you actually need to configure your distributed configuration information service. Now the configuration for etcd is really simple. We've got a scope, we've got a time to live, we've got the host. If you actually have authentication set up in etcd of some kind, then that information will be there too. Zookeeper configurations tend to be a little bit more complicated. There's an example of that in the docs of the different elements that you need for a Zookeeper configuration. So that's where you configure what etcd cluster it's connecting to, as it needs to be configured on each individual node. Then you actually need to configure a bunch of things about PostgreSQL. Now, one of the reasons that you need to do this is if Patroni is initializing your Postgres cluster for you, then the configuration you put here is the only configuration there is for PostgreSQL. Because it needs to be able to rewrite the configuration in order to restart. If you're retrofitting Patroni onto an existing database cluster, then it might be a little bit more complicated and you might be able to ignore some of this stuff. But if you're doing it the way that I just did it, let's spin up brand new containers, et cetera, then all of your Postgres configuration comes from here. And this is all of your typical things for Postgres configuration, including, listen address, again, the advertised connect address, which might be different, the data directory, maximum lag on failover. This is, we do a check, again, through the API of how far behind are you? And so in addition to trying to choose the furthest ahead one, you can also set a threshold, and by default you do, saying, hey, if the replica is this far behind, don't fail over anyway. Probably in production you'd want to set that more to something like a gigabyte, or more depending on what your traffic is. And then the rest of this is actually, create replica methods. And I'll mention this again later on. By default, we use PG base backup because it's the simplest way of spinning up new nodes. We do actually support other methods, Postgres point time recovery, WAL-E recovery, in order to deploy new nodes. Say if you might have a larger database for whom doing base backup is prohibitively slow. So one of the things that I'm actually working on is a modification to allow you to take the base backup from one of the other replicas, which is not currently supported, but it will be supported in the future. The other thing that you actually have to set up is your host-based access, your Postgres access control file. Again, this needs to be written by Patroni if Patroni is initializing the database cluster. We set a whole bunch of passwords because, again, we're initializing the cluster and those passwords need to be set. And then if you need to pass any parameters to Postgres, like, for example, if you're doing archiving, parameters for replication, et cetera, those are going to need to be passed via Patroni because Patroni is writing it's actually not writing the PostgreSQL.conf. It passes these things on the command line via Postgres command line options. Yeah?
Back up just a little bit. Do you have to use the all trust under authentication? Or under PGHBA? So that's just saying full trust.
I'm trying to remember we did that. That was a bug I filed early on. Okay. When we initially initialize the cluster, we have to launch it in trust mode so that we can create the passwords. Okay. And it wasn't getting relaunched, and so as a result, we were locking ourselves out. I think now you don't actually have to do that. In this case, because it's a container with no SSH, it's perfectly fine to say local all trust because no one can get into it, right? Unless they can hack the container, and if they have root access on the machine, they can get into it anyway, right? So in a different circumstance, you might not want to do that. So it would be worth testing, and if not, add your thing under this bug and say, hey, it's still not fixed.
So if you're doing that on
yeah.
VMs that have SSH access to them.
Yeah, then, and part of it depends also as, are you initializing this via Patroni or not? If you're not initializing it via Patroni, then it's not important to have local trust access because you will have set these passwords. Do you follow me? Yep. Rather than Patroni setting them for you.
Sure.
Okay.
So if you don't write your config file in Patroni ease, could you just use include?
Yeah, so I actually was working on that and I discovered a problem with Postgres, which is we can't pass include directory or include file via the command line in Postgres. It has to be in a Postgres.conf physical file, which is kind of a pisser because it's not in the default file. See my long arguments on hackers about why conf.d should be default behavior in Postgres, and which I lost. But so anyway, so yeah, and so that was the idea, is that like you would actually set it up. I was looking at a modification for having a conf.d file. I might put that in by default in the future with Patroni. Would be a conf.d file. If you're doing containers, you would mount that as a volume. If you're doing it in a VM, you'd do it wherever you wanted to, and then you can actually have another place to drop in configuration options rather than passing them in the Patroni command line. The advantage of passing everything through the Patroni config file is that you basically have one master config file to rule them all that can get checked in under whatever configuration management is, and then you don't have to worry about having several separate configuration files. Might be an advantage, might be a disadvantage, depending. So, let's go ahead and do that again. Okay, so let's shut this down. Okay, and I actually need to tear down the containers. The reason I need to tear down the containers is because if I don't tear down the etcd container, it'll just restart it. And the etcd writes stuff to disk, so it already has master marked as initialized. Actually, no, if I did this, so there are circumstances where Patroni can be unable to restart without human intervention, which is if etcd is down, and then all the database nodes shut down, and then they come back up, and there's no master. And you don't have a well, no, except if you don't have a valid ETZ cluster, you're not on there anyway. Anyway, restarting it multiple times. Here, I want to actually restart it from scratch. So, we're going to restart it from scratch rather than under failover circumstance. So again, we get lots of output. You can see all this stuff. The failed to acquire initialized lock is so there's two kinds of master locks, right? There's the I am the current master lock, and there's the initialized lock. The initialized lock is held for the entire cluster, and it's only set once. Once it's set, it lives under that cluster namespace in etcd until it gets deleted. And the reason why is you don't want to accidentally reinitialize a database cluster that has data in it. You can actually get, I'm trying to remember the specific sequence of events because I've done it. You can actually get wedged under circumstances where the Patroni cluster will refuse to start in read-write mode because it can't find an initialized master, but the initialized lock is still set. We decided that was better than having it wipe out all your data automatically. But that would be under a circumstance where everything went down and then sort of came back up again unevenly. And those are hard to protect against 100%. So we see this going on. I don't understand why when I start this particular demo, 2 always wins. I don't know why. Because it's actually the second one being started, but for some reason, the timing of it, 2 always wins. So. Oh, wait a minute. 2 always wins, but doesn't this always have the same IP address? Oh, it's 3 this time. Okay. So again, here we see node 2 has 2 replicas, nodes 3 and 1. So that's our initialization setup. And so then we want to go ahead and kill 2, right? And you see all of this traffic of stuff, not being able to connect it and that sort of thing. Actually, at that time it failed over really fast. Part of it depends on the timing. You've got a 10-second polling interval, right? And it depends on whether you hit that interval immediately or later on. And then we get this. Now, there's no contesting who's furthest ahead because I'm not running any traffic on this cluster, so they're all co-equal points. So we have a failover, and now we have 2 nodes. So who's the leader this time? 3. 3 is the leader. Well, it's either going to be 4 or 5, so let's find out what it is. Am I the leader? No. Oop. There we go. So 1 is replicating from 3, right there. And so now we actually want to bring a node 2 back up, or bring a new node 2 up. Actually, hold on. Let's actually wipe out node 2, huh? Because under a circumstance where you had a real failure, you wouldn't be bringing back up the original node, right? We want a new node 2. So now we're going to go ahead and bring node 2 back up. Hold on. Okay. There we go. And node 2 has connected. And we now have 2 replicas. This time, 2 and 1 are replicating from 3. Anything else we want to do to this cluster? It's all temporary containers, so we can, if we screw it up, I'll just rebuild it. Ah, that is a very good point. Yeah, let's do that. Yeah, so you see all of these sort of reconnections, that sort of thing. So you demoted self because DCS is not available. That's the message you're getting. The original master is restarting as a read-only node. Because the thing is, Postgres, you can start any node as a replica of a non-existent master, at which point it becomes a read-only node. And because we support cascading replication, it doesn't require breaking replication to the other 2 nodes. So I'm going to keep getting this message, of course, because it's still trying to connect to etcd. Now, if we bring back up etcd, ta-da. Okay, let's see who's the master now. Oh, no, 2 actually promoted itself. That's interesting. Oh, right, because the TTL had expired. Yeah, so that'll happen if the etcd cluster goes down, when you bring it back up, you may get a failover even though it's not strictly necessary. And that, again, is a timing issue, right? Because if the etcd cluster has been down for longer than the master lock time to live, then when it comes back up, the individual node doesn't know the difference between the master being completely down and the information service having been down. And so it treats it as a master election circumstance. Now, in this case, because all of our nodes were read-only, we lose no data, because the nodes will have been at the same replay point at that point anyway. So that's why it was not regarded as an issue for us to fix, because it's not really a problem. Now, if I brought etc down and then I deleted it, we would actually never come out of read-only mode, because it would keep pulling for the list of servers and it wouldn't find them. So we're getting towards the end of our time here. I've already taken a lot of questions, so let's actually finish talking about the other stuff here. So what's included currently in Patroni? 3 things: the Patroni agent, which again runs on each server, which has a RESTful API. There's also a rudimentary command line tool that's under heavy development called Patroni CLI, that is steadily improving to have its full sort of spec of features, but isn't complete yet. Patroni CLI is just basically, again, a Python command line tool that allows you to do things like interrogate the API, the individual nodes, to ask them for stuff, and importantly do things that wouldn't happen automatically, like, say, manual failover. Like, say you want to manually fail stuff over because you can apply kernel updates to individual nodes, right? So you want to do manual failover. Or if you want to do manual failover because you're put node on a VM with more memory or whatever. So also to stop individual nodes, et cetera, you can do that via Patroni CLI. Stuff that's not included. Now, I mentioned that the third part of failover is to fail over the applications. That is not included in the core Patroni project. And the reason for that is that it's going to be provided by other things. There's no GUI interface for Patroni, and I don't think anybody has any plans to build one. Deployment of containers, et cetera, VMs or whatever, that's your own thing to do, or do it via downstream projects. And there's no built-in monitoring, except that the APIs do provide a lot of information. So a monitoring system can interrogate the APIs and get a lot of information for monitoring. We just don't have any templates set up for that. So, given that Patroni doesn't cover everything, we have a couple of downstream projects. The one that is sort of in production right now is a project called Spilo from Zalando. So Spilo is Patroni plus a whole bunch of Amazon tool orchestration. They're a very AWS integrated company, and so they use all the AWS tools, you know, the Amazon virtual IPs and the load balancers and that sort of thing, on top of Patroni to provide a complete system. And that's available from their stuff with documentation. If you're actually going to look at implementing Spilo, though, be prepared to devote a significant amount of work time to it. It's a complicated system with a lot of parts, and it's only ever been deployed at one company. I mean, they have done a really good job of trying to document it, but it is very complicated. The one that I'm working on, but it is not available yet, but, you know, check back in a month or so. I'm nicknaming Atomic DB. I'm going to be using the Atomic/Kubernetes stack to supply more of a complete system, again, on top of Patroni with Kubernetes and service discovery in order to provide the routing and failover portion of the whole thing. And also maybe provide some OpenShift containers that are Patroni-based for anybody who uses OpenShift. So check back in a month or two, or just follow my blog, and you will see that as it develops. More features. There is PG Rewind support. So if you're okay with wiping out data, you can enable PG Rewind, which means that down nodes will be guaranteed to be able to rejoin the cluster, but that may mean that you're wiping out data that they contain that's not on any other node because of failover. Again, I said we do have configurable node imaging via WAL-E and point-in-time recovery. There is instructions on how you would enable synchronous replication support. Like I said, I don't think that's really tested, so you might want to do some testing. And we also now have ways to flag specific replicas as non-failover replicas, which is something you'd want to do if, say, you have 20 replicas for load balancing. You'll generally want to have like 3 or 4 designated failover replicas that don't take load, and the rest of the replicas are going to be load balancing replicas. Other things under development, cascading replication support. Obviously for geographically distributed stuff, you'd want cascading replication. In integrated proxy, somebody actually wrote something in Go for another project that I was looking at potentially integrating because it's a nice little proxy that will query etcd or Zookeeper to find out who the current master is and reroute stuff. And then when bidirectional replication actually becomes a thing that mere mortals can install, we'll want to look at supporting that. But in the meantime, if you see features that we don't have and that you want, it's on GitHub. It's mostly Python. You can fork it. So here's a whole list of resources, as you can see for this. You can get this, you can either take a picture of the slide, or I will be pushing this to my GitHub page, jberkus.github.io, after this presentation, and then you will have all of those links. Yeah. So, this isn't pushed yet, but it'll be pushed within the hour. So any final questions before we actually, we got 5 minutes for questions. So go ahead, we can even like clobber the cluster if you wanted to. Yeah? Yeah.
There's a test suite as part of this code, right?
Mm-hmm.
Is the demo that you just did related to that, or is it completely separate?
So the demo is separate. So the thing is that the test suite related to the code is unit testing, which is great to have, but it doesn't test some of the things that we want to test, like does failover work? And that was the reason I created the Patroni Compose project, which is what I'm using here. Oh, actually, I don't have a link to that. I'll link that. I will definitely link that off of my webpage. The Patroni Compose project is a Docker Compose file that is designed to set up a cluster so that you can actually run automated test things on, like, does it failover work? Can I add a node, et cetera. That needs to be built out into a full test suite of failover behavior, which doesn't exist yet. So that's one of the things that we actually kind of need. I'll probably be building that out also via Kubernetes, is that once I actually get up Atomic DB, we'll have Kubernetes, and that will have its own test suite built into it, because it's going to be a little bit easier to automate than what I've got with Docker Compose, which is a little rudimentary. So yeah, you had a question?
Yeah, if this isn't a long time answer, it does make it
Yeah.
offline or
Yeah.
requires beer.
Yeah.
But PG Pool 2 performed similar things, but it wasn't really mentioned.
Yeah.
In the talk, and there's probably very good reasons that I don't have the inside.
Okay. Well, all I'm going to say about PG Pool 2 is I don't talk about PG Pool 2 because I don't want to trash other people's code in the community. I was just say, I would personally not use PG Pool 2 for automatic failover. Other questions? Okay, well, thank you very much.